Modern civilization runs on measurement. From the supply chains guiding cargo ships to a commercial flight shaking blindly through heavy clouds, we rely entirely on instruments to tell us exactly where we are. But the moment those instruments lose their line of sight, when a submarine dives or a drill breaches deep underground rock, our mapping systems fail. We go completely blind. The barrier defeating our technology isn't a lack of processing power. It is an inescapable physical wall built by ambient vibration and thermal energy. This wave graph shows exactly how that barrier works. A smooth, faint target signal enters the system, but it is swallowed completely by violent, chaotic static. Engineers call this the noise floor. Every classical electronic circuit generates this internal interference. Because of that static, our current sensors act like massive, heavy bells. You need a sledgehammer of a signal to make them ring. Anything faint or subtle, a microscopic magnetic shift or a deep subterranean void, is masked by the noise. For decades, the engineering fix was simple: build a larger, more powerful machine. But we have reached the absolute physical limit of that approach. To detect the quietest forces on Earth, adding mass to our electronics doesn't help. The very size of our machines is exactly what keeps us in the dark. To bypass that static, we abandon the macro world entirely. Zooming down past the microscopic level, we enter an environment where physical laws go silent. Here, engineers ignore the clarity and hardness of synthetic diamonds. Instead, they rely purely on the stone's incredibly rigid internal geometry. This diagram shows that internal structure, a pristine carbon lattice. It is a perfectly uniform grid of atoms, locked tightly together to block out external vibrations. Inside that grid sits a deliberate mistake. Engineers remove a single carbon atom and introduce nitrogen, creating a nitrogen-vacancy center. It is literally a missing piece in the crystal. That tiny pocket of empty space acts as a perfect trap. It catches a single electron and holds it in a quantum state, completely insulated from the crushing heat and noise of the outside world. Remember the heavy bell needing a sledgehammer to ring? This isolated atom is the exact opposite. Suspended in its quiet diamond vault, it is so undisturbed that it reacts to the faintest physical stimulus. It functions as a hypersensitive compass. When a microscopic magnetic field passes by, the trapped electron instantly shifts its orientation to match. A sensor built from these diamond flaws can detect the magnetic field generated by one single human neuron firing inside a brain. This side-by-side image shows the difference. On the left is the blurry guesswork of a traditional medical scanner fighting through the noise floor. On the right is a neural pathway mapped by a quantum sensor, capturing exact cellular activity. By harnessing a flaw in a diamond, we stop guessing what lies beneath the static. We simply feel the physical world as it actually is. Taking this extreme atomic sensitivity out of the medical lab and scaling it up solves some of our most critical industrial blind spots. In 2026, research teams successfully applied this isolation technique to measure something far larger than a magnetic field. They measured gravity. This diagram shows a quantum gravimeter. Instead of bouncing waves blocked by solid matter, it feels shifts in local density. Passing through rock, it highlights hidden voids. Engineers mapped an entire facility through granite, measuring only the missing gravitational pull. Now apply that capability to the submarine from earlier. The moment it dives beneath the waves, its GPS cuts out entirely. Equipped with a quantum sensor, that same submarine can match its local gravity readings against a predefined map. It can navigate the deep ocean for an entire year, maintaining centimeter precision without ever surfacing for a signal. For the last 100 years, human progress relied on manipulating the electron. That force gave us the silicon chip, the computer, and the internet. But the electronics we built generate too much heat and too much interference. In our pursuit of absolute precision, the electron has reached its physical limit. By isolating single atoms inside a diamond lattice, we step past that limit. As we transition from the age of the electron to the age of the atom, we are finally opening our eyes to the unseen universe.